Hi, everybody. Really good to see you here in this beautiful, beautiful Microsoft office. Today, we're going to talk about manufacturing and AI infrastructure. You know that 100 years ago, a little bit more, the invention of assembly line and the whole process changed the manufacturing world and changed the world after that, as we know how we build products. And today, AI software and robotics together, they are on the edge of another revolution. And we've seen in the last few years how AI tackles writing poems, creating art, coding some mini games. But the real change is happening when AI touches physical world. And that's what we're going to talk today about. If you look at the numbers, the opportunity in the US at least is $10 trillion, according to Morgan Stanley. But think about this. It's like 20 times more than any huge announcement in the last few years, like you think about Stargate or anything like that. And we have a decade to realize on it. And to realize on this promise, you need both AI software and robotics. And today, I'll give you a glimpse and like a sneak peek how it looks like, and not actually in the future, but today, because we've been doing it for 7 years on Bright Machines. But before that, let's look at the facts. So we have the biggest sectors of economy. You can look at this slide here, like from AI infrastructure to aerospace to manufacturing, depending on really high, complex, high-value electronics. And the reality of today is like 2/3 of that electronics is being assembled in Asia, mostly in China and other Asian countries. Why is it a problem or like a challenge? The thing is, they assemble it like you see it on the left. That's the lines assembling mostly phones in this case, but other electronics as well. So automation has been being introduced like really in a slow pace. And why you do it like this, you depend on human labor. And if you look back in the US, it's only 8% of labor force in manufacturing here, so we don't have enough labor. More than that, you know all the disruptions since COVID and then geopolitics in the middle of the supply chain, and you cannot depend on different regions in the world if you're trying to protect your own economy. And then finally, when you do assembly, like you see here on the left, and you depend on people, you don't have data. When you don't have data, you cannot run a cycle of continuous improvement, and you cannot create additional efficiencies. So the question is, how do you solve this? And the answer, of course, is, in the last few years, you take AI approach and software, in this case, AI models. And I'm not speaking about LLMs, but like the different models for maybe automation and robotics, foundational models, and using machine learning in that environment. You take robotics that's going to help you build and actually replace those tedious tasks that usually human labor had to do in China. And then finally, you leverage that compute infrastructure to give you power. And today, we're going to also talk about how you build this compute infrastructure using those methods. And so right now, I promise you a sneak peek. And there's going to be a lot of video material in my talk to make it entertaining. What you're going to see here is our cobot solution that builds NVIDIA DGX H100s. OK, it's working. So you can see the scanners, the cameras behind it. You have AI models that run it in real life. You put 2 boxes in front of the robot. One comes with this H100 cluster. It's around 60 pounds, so really heavy. The way you usually build it is like a two-person team. And then we're going to change what we call end-of-arm tool and going to connect that GPU cluster to the server chassis. There are like 17 screw-driving operations, really precise. You can imagine like if you break something and you break part of the board of H100, H100 cluster itself is like $250,000. So it's really important to build it precisely. And we call it zero scrap operations. So in this case, one robot replaces several human workers and creates a zero scrap operation with 100% yield to build GPU clusters that power the economy of the future. Speaking about Bright Machines quickly, we are 7 years old. We're based in San Francisco. We build AI software and robotics that actually powers this manufacturing economy. We work and focus on what we call AI backbone or infrastructure for data centers. So you can see a few of our customers, investors, partners here on the slide. We have technical workforce. Our headquarters in San Francisco works heavily on R&D. And we build anything from GPU-based, CPU-based servers to networking equipment and data storage. And the way we think about how you change manufacturing the product is not only about the assembly. Quite frankly, it's about starting with the design, because when you can impact the design, you can create a much better design that is much easier to be automated by robotics and use for that software. So you start with the simulation, and we work closely with NVIDIA Omniverse on the simulation piece that actually leverages Azure of Microsoft. And then when you do the simulation of design, you build better lines and better product itself. Then you start introducing it to the lines, you build those products, and then 3 years after their life cycle in the data center, you have to disassemble it too, because you want to be sustainable and protect the rare earth minerals, for example, extract them, reuse, recycle, resell. To show you the way we think about this, we'll start with what we call Bright Designer. That's the product we actually launched a few months ago at NVIDIA GTC conference. You can see it's photorealistic simulation of our robotic cell plus the new design of the server that our customer is designing. And then we can simulate different parts of how it's going to be assembled. And you're going to see the use case of memory module insertion into the server. And you can see the clearances. You can test whether it pushes the heatsink, for example. You can also test in the future and add physics, materials, and other things. So it's pretty cool to do that in advance before you finalize the design and push it to manufacturing, because historically it's kind of separated the design engineers and manufacturing engineers. And here you can see an example of our line. It's also being simulated in the facility, on the floor. It's just an example of how the engineers and manufacturing and design working together in the tool. But the idea here, again, is like when you build or you design the line first, and then you actually build it in physical world on your floor in any part of the US or the world, for this matter. The next one is, we call it smart skills. So what's behind the capabilities of our assembly? That's the machine learning algorithms that run new product introduction. What you see here right now is like the 3D model of the server and how robots see it. And again, now you can see not the simulation, but the real video of physical world of the same use case of assembling and inserting memory modules into the server chassis. It does the dip just to test it as a demo, and then to show you the flexibility, we change the angle. So we put a metal brick, change it to 15 degrees, and you will see that the robot is going to change the angle as well without destroying or any damage to the board, and continue assembling. That's really important because we operate on the 75 micron precision level versus some other companies like Waymo you can see like in physical world. The other thing we do is we were running the same pipeline for inspection as we do for navigation. Also powered by machine learning. You will see the several use cases. One classification, for example, when you insert the element, is it fully inserted or not? And you can see it by color. And then you can notify a computer or operator about this. And then the other thing is inspection for debris, pre-assembly and after assembly. For example, sometimes people, when they build servers, they do leave screws and wires in the server, and that goes all the way to the data center. You're trying to avoid it. And here you're going to see the heat map that visualizes where you have the screws and where the problem is happening. So next one is it's like lagging a little bit. Microfactory overview. So you saw our microfactories in the simulation environment, right? This is more of to show you the idea of how modular and scalable the microfactory is. We can have multiple robotic cells. They can be closed like this. You also saw a cobot, the green guy who was building NVIDIA H100s. And then you can put them and mix them together depending on what you're trying to build and what you need to build that product. Each part of the microfactory, each robotic cell represents a skill. For example, insertion, pick and place, labeling, or something like that. And then putting them together, you can decide I need to add a few more steps. They are automatable right now. You extend the microfactory, and then you can build more steps of the assembly process and better quality products in this case. And all of it, of course, is powered by our software that we call Brightware, as we discussed before, powered by smart skills. The next thing I wanted to show you is the server disassembly. We talked about assembling, designing, and then finally, at some point, you need to disassemble stuff. So what you're going to see here is like the same robotics that we have powered by the same software. But what we do, we're going to disassemble parts and extract heatsinks or CPUs, memory modules. The funny thing here, you will see how we extract a CPU with several clips on top of it. Usually, it's fully manual, human-based activity because it's really hard for a robot to unclip it and extract it. But you can see how it's pretty entertaining to look at this. So you put the clips out, and then you're going to take a CPU out of the server, and then you're going to sort it, and then you can decide as a company whether you're going to resell, maybe reuse, or maybe destroy it for precious metals. And after this, you're going to do the same with your memory modules. In most cases, memory modules are usually in a really good shape, and you can resell them to other smaller companies, or maybe sort them to some other countries, or even reuse in your data centers in the future as well. So putting this all together, you can run your manufacturing from one place in any place in the world. In this example, we just showing, like, for example, we have several waves of implementing new types of lines powered by robotics and software in different parts of the world and the US. And the idea here is you can sit in your office with R&D and design a new type of data storage or GPU or server. You can simulate it in the simulation environment that we built with the help of like NVIDIA and Microsoft. You can then push this product to introduce them and run on the test line, maybe in your headquarters. And after this, from this control tower, you can push it to different microfactories that you have around the country or around the world instantly. The big difference here is that today, when companies, like big companies like Apple or others, they need to introduce new products and build them and test them, they fly their engineering teams around the world to those countries where they build it. Either it's China or India or any other country. And it takes usually weeks. The way we already introduce new products, usually it takes, we create a 3D model within 4 hours, and within the day we run and test it, and then we can push it to our stations and lines on the ground in different states or countries. So we already pushed from like weeks to a day, and then in the future, when you run a simulation, you can push it even to hours, because then you don't need to create a physical model, wait for it to scan, to introduce, you just push it straight to the lines. And that creates a big, big change in terms of speed, efficiency, and scalability of manufacturing. And it's going to be a huge help for the economy of the United States with all the initiatives that are being taken place right now in this country. And then I want to finish with one video that actually gives you a clear perspective of how it has been done before and how it's already done today. What you're going to see is left and right. On the left, you're going to see how it was assembled previously in China and Asia. And on the right, you're going to see our lines that are located in the state of New York that are assembling the energy storage units. And here you're going to clearly see the difference in terms of quality, precision, speed, and any other element. So it's pretty cool. There's real speed comparison. On the left, you can see the manual labor of how manually the energy storage units that can go to schools, data centers, and other places are being assembled. And on the right, you can see our robotic cells that are doing it with the help of robotics and software in an automated manner, tracking the data quality and doing it at great difference in terms of speed. So again, each step is a different robotic cell, so you put them together. I think this is one of our more complex lines. We have like 16 to 17 different cells put together, and we have like several lines located in the state of New York that are building those energy units already. And plus, again, as I mentioned, we operate in different states with building servers and data storage and so on and so forth. Here, I think I want to say thank you. Thank you for your time. I hope it was like entertaining and informative. And we really believe that AI, software, and robotics is the huge answer to this physical AI and how it can change the whole economy of this country and the whole world. And we will be able to build and do more in physical AI with AI and robotics in the really near future. It is changing at a really high pace. Thank you.